to review here. You all know what an integral is. I just want to go over what is Riemann sum, because Riemann sum is kind of the basic idea of numerical integration. So you have some function here. Again, you're as we've done many times, if you want to integrate, you're discretizing. You're dividing your axis into intervals, into points. Just the same thing you did with splines, same thing we did with a bunch of different applications. And then you're trying to approximate on each interval. Now you remember an integral means an area. That's what an integral means. So the integral of this function, let me grab this and put it here. So if I consider this function, whoops, sorry. So the integral of this function would be the area underneath, right? So, okay, so the integral equals area. Okay, now the simple-minded way to approximate this is to use bars, right? So, but there are a couple of ways to use bars, right? I can use the left-hand endpoints. On this interval from 0 to 1.1.25, I can approximate with a bar of height equal to the left-hand endpoint. So that would be this here, right? This here, and this here. So that's left-hand endpoint. You could do the right-hand endpoint, which would give you a different result, right? So the right-hand endpoint would be the right-hand endpoint. Here I would have a bar of this height, right? Because the right-hand endpoint is here, and here, and then here, and then here. So naturally you're going to get very different answers, and the answer is going to depend on the shape of the function. Here you can see that the right-hand endpoint gets you a higher estimate than the left-hand endpoint, but that's just because the function is increasing, right? If the function was decreasing, it would be the other way. All right. So these are two different estimates. And you can prove that if you have a continuous function, if the function is continuous, then both methods converge to the actual integral. As the step size goes to 0. Okay. All right. So, but you can see here that practically these are extremely inaccurate, and it's logical, instead of doing the upper or the lower, to kind of do a linear interpolation. Do a piecewise linear interpolation and try to use that to get your area. So I can just say smarter way to approximate the integral. You can use linear interpolation. All right, so let me grab that picture again and see what linear interpolation would give us. Okay. So linear interpolation means actually use these blue lines. I mean, the actual curve is going to be smooth, right? We can use these blue lines as a guide to find our area. So in this case, we would take use the straight lines. And you want to find the areas under these trapezoids. It's called the trapezoid rule because these are trapezoids. So we want to approximate the actual integral by the area of the trapezoids. By the sum of the areas of the trapezoids. All right. Now, how would you get the area of one of these trapezoids? So let's look at a single trapezoid. So the single trapezoid, here we have an interval like this, and let's see, he calls what he calls this, he says this does x, but the way he indexes it, he call this x0, x1. All right, so it's just say, let's just take one particular interval, xi minus 1 and xi, right? Then this would be f of xi minus 1, and then this would be f of xy, right? And then the trapezoid is going to look like this. So if I want the area of this trapezoid, basically you can kind of think of turning this into a rectangle by taking this top triangle, flipping it over, and putting it onto the other side, and making a single bar. So you want to take basically the average of the heights times the base. Okay. So you take the average height times the base.
Is that essentially just a square with a triangle on top of it?
Yeah. So I mean, the way I look at it is, if you think of this as made of water, something like that, and you even it out, then the even level would be halfway between these two. Right? So it's going to be f of xi plus f of xi plus 1 over 2 times xi minus xi plus 1. I'm sorry, other way, xi minus 1. Let's give myself a little. Sorry. Okay. All right. Now, what an important thing to think about is, what is the error? And he does talk about this. Okay, and I don't want the exact error, but I want the order of the error. What does it depend on? So let's suppose. So we'll let xi minus xi minus 1 be equal to h, and that's going to be small. Okay. So I can do a Taylor expansion. I don't think he does it this way, but this is really the way that a numerical analyst would do this. So I can do the Taylor expansion. And the Taylor expansion I would get would be f of, and let me choose my point. Let's just choose xi minus 1 as my point of expansion. So f of x would be equal to f of xi minus 1 plus x minus xi minus 1 times f of prime of xi minus 1. Okay. Plus, and then I'm just going to write plus O of x minus xi minus 1 squared. Okay. Now on this interval, the distance between x and xi minus 1 has to be less than h. Okay. So this here is going to be less than, this is going to be less than or equal to, h squared, to h squared. Okay, so this term is less than or equal to h squared. Okay. So what I have here is my actual function. If I integrate, I'll get f of x. If I want to, because what I'm trying to find is the integral. If I integrate this from xi minus 1 to xi of f of x, that's going to be equal to, now if I integrate this constant, I'm going to get f of xi minus 1 times h plus x minus xi minus 1. Well, let's see, if I integrate this, if you integrate this on this interval, this is a linear function, you're just going to get, and then this is 0 at the lower endpoint. You can think about this, but that's actually going to give you h squared over 2. And then this is going to be f prime of xi minus 1. And then this is going to be times, let's see, what am I doing here? I think that's it. Is that right? Because that's going to be this.
If you integrate f prime,
F prime's a constant.
oh, it's a constant.
F prime is a constant. That's the whole point of Taylor series. So, I'm going to get this. So that's xi minus 1. You can't even read that. Okay, and then here I have plus. Now, if I integrate this number that's of order h squared over an interval of order h, then this is going to be order of h cubed. Okay. So what this is telling me is that if I use a linear approximation to my function, and I integrate that linear approximation, my error has order h cubed. Okay? So that means, so the important conclusion here is that a linear approximation to f of x on the interval xi minus 1 xi will produce an error in the integral of order O of h cubed, where h is equal to the step size, and that's equal to xi minus xi minus 1. So for each interval that I integrate over, I'm going to have an error of order h cubed. But now the question is, how many intervals, how many steps do I have? Okay. If I'm integrating from a to b, okay, and I'm dividing these into steps, and each step is h, then how many steps are there? That's right. B minus A over H. Right, evenly divide, you know that you've got 1 inch is 1/12 of a foot, so you have 12 inches. So there are B minus H steps. Now each step has error O of H cubed. Okay? So that means the total error for the total approximation is equal to B minus A over H times O of H cubed, and that's the same thing as, I can just write that of O of H squared. Okay. I lose the B minus A because I'm only concerned about how it depends on H. Okay. It's some constant, that's what the big O means. So I can say, i.e., some constant times h squared. Okay.
So I have a question.
Right.
Going back up to the
Right.
Integral,
Right.
are you taking the integral twice?
No.
Then why have the integral sign right there? And
Okay. Well, no, I'm sorry. No.
Equal.
Yes. So this
Okay.
is dx. No, you see, this was the function.
I think she didn't see
No.
that equal sign as an equal sign.
No, I thought that was a C. That's
Okay,
why I was
okay.
confused.
Okay, sorry, let me write that a little bit. Yeah, that's let's make it, sorry, let me make it a little bit neater, just to make it, now it's here, so just make it a little bit more legible. So I mean, the point is that I was integrating this, if you can recognize, this here is the integral of this term. And
That's
then
why
this
I
here
was
is,
confused, because I thought you were integrating it for.
no.
I got you.
Okay, all right. So, I mean, this is what you would call, it's kind of back of the envelope. I'm not being very careful because all I want is how the error depends on H. That's all I want. And this was the important result. So the error is some constant times A. So in other words, if I use twice as many steps, then what happens to the error? The error gets bigger when you have use more steps?
It gets
Now think about it. If you have more steps, what happens to H?
smaller.
H gets smaller. Okay, so if H gets smaller, what happens to the error? It gets smaller by how much?
H squared.
All right, yeah, so I've divided H by 2. So what does that divide the error by? Well, H gets divided by 2. So H squared gets divided by 4. So the error goes down by 4. Okay. All right, so I'm going to do this now because I think this is important. This is really very clever step that somebody took, and it's a common technique in mathematics that you would call is basically extrapolation. So suppose I use n steps. Then my estimate. So let's say let's let IS equal the estimate with n steps. I'm sorry. I should say IS of n. Sorry. So let's say IS of 2n is equal to the estimate with 2n steps. Okay. Now, so IS of n, I'll write it this way, IS of n is equal to the I actual plus epsilon, and this epsilon is the error. Now, what about IS of 2n? What happened to the error? Okay, so now I should put approximate because it's not exactly, but roughly. Okay. Now, the amazing thing is that now I can use both of these to improve my estimate. Because I know this, I basically have two equations and two unknowns. I don't know the actual and I don't know the epsilon. But I can use these two equations to get a better, and this is, again, this is, I should say this is approximate, but it's a good approximation. It's a good approximation, okay, right? So I have, so these two are, this is unknown. This is unknown. This is known, right? This is known. This is what you would compute, and this is also known. So I can go ahead and solve for I actual. In fact, the best way to do that would be multiply the second term by 4 and subtract, and that gets rid of the epsilon. Right? It's just cancellation. Okay. So let's do that. If I take IS of n, so this is the same thing, I actual. Sorry, actual. Plus epsilon. And then I'll take 4 times I est of 2n. And that's equal to 4 times I actual plus epsilon. And then let's do minus this, and we'll do plus this, just to make it nice. So I can get 4 times I est 2n of 2n minus I est of n is equal to 4 times it's equal to 3 times I actual, right? And then here it's this plus, I guess what I'll do, something smaller. So I'll say very small. It's even smaller than epsilon. You get it's the error in the epsilon, which is a really small error. Okay?
So it's so small that it's negligible?
It's so small that it's much smaller than the original error. It's never negligible. If I was more careful, I would give a more accurate estimate of this. If I was more careful. All right. So I can.
Do we know enough to do that? Do we know enough to?
Well, yes, we could. I may give you that as a problem. Okay. So that means that I actual is approximately equal to 4 times IS of 2n. Okay. Minus I est of n over 3. Okay, plus very small. Okay. Now this is the Romberg formula.
So one of the epsilons cancel each other out.
Sorry?
One of the epsilons cancel each other out.
They do, largely. So notice that here I should say, again, I should put this here as this is approximate. The errors did cancel each other out. See, there's no epsilon here. So instead of just small, I should say smaller than epsilon. I should say very small. So these epsilons, they mostly cancel.
Shouldn't you be subtracting whatever the small is in the bottom? If you rearrange that.
In the numerator, back in the numerator.
Well, you see, I have a minus here and a plus here. So this is a.
I'm saying when you went down the red box to get to that equation,
Yes.
it should be minus small, right?
Well, it's minus very small is still very small.
Right.
Okay. Okay. That's the same thing. Notice that I
I was
played.
just making sure I didn't miss something.
So minus very small is still very small.
Right.
Notice here when I was doing order estimates with h, in fact I multiplied by b minus a over h, and I said O of h squared. So constant factors are not changing the order of magnitude. So you're just saying roughly. I mean,
Right.
5 times 10 to the minus 9 is still basically 10 to the minus 9. It's that order of magnitude. So we're looking at orders of magnitude.
Right.
Right, Right, but he's saying if you solve for the actual, don't you subtract small rather than?
Yes, that's right. I'm saying positive, very small. Very small, it
It's so
doesn't worry
small
about the
it doesn't
sign.
matter, yeah.
It's something. It's something positive or negative. I don't care what the sign is.
Okay.
In fact, I don't even know that it's positive here. I don't know if it's positive or negative. So there's no point in keeping track of any signs. Okay. So so this is Romberg integration. Whoops. And the thing that's wonderful about this is that you get additional accuracy basically for free. Now, why do I say for free? Because when you compute this estimate with 2n intervals, what do you need to calculate? You need to calculate 2n values of the function. That includes these values. You're using the same values. You're not having to calculate any more functional values. So you're getting something for free, basically. Okay? So you don't need to calculate more values of f of x to get a better estimate, a more accurate estimate. You're just using your data smarter of the interval.
Right, this is not a case of iterating till our tolerance is we're below a certain tolerance or something like we do some of our programs we just do it once.
Well, I mean, if you did want to reach a certain tolerance, you'd have to iterate this method. You would have to iterate this method. You'd have to divide your interval again, but you can still use Romberg on that smaller interval. So you would indeed iterate. All right. So this Romberg is really the name of the game, and all of the integral stuff that you'll be doing is basically trapezoid with Romberg repeatedly applied to it. All right. So you may have heard about Simpson's rule. I think did anybody remember seeing Simpson's rule? Yeah, it should. So Simpson's rule says instead of a piecewise linear approximation, you use a piecewise quadratic. Use a piecewise quadratic. Now, this is not quite the same thing as quadratic splines. Let me explain here. If I have several intervals here, if you want to use Simpson, you actually have, basically you have even and odd nodes here. And if your function is like this, okay, what you do is you divide if this is my A and this is my B, I divide the interval like this. And I do a quadratic here. So this would be a quadratic. And then this would be another quadratic here. And then this would be another quadratic here. And then this would be another quadratic here. Well, let's do a different color. This would be another quadratic here. Okay, so this is also quadratic. So for every two nodes, you have a quadratic piece. You have a quadratic piece. And the reason you do that is that you know that 2 points determine a line, because the line has 2 unknown constants. 3 points determine a quadratic, because a quadratic has 3 coefficients. So you need 3 points to determine a quadratic piece. So okay, so you have a quadratic piece here. Actually, this was not quite so accurate. This point should agree. These 3 points, the quadratic is interpolated between these 3 points, the midpoint, and these two. This quadratic here is interpolated between these 3 points, this midpoint, and these 2 endpoints. So this is a quadratic function that interpolates those. This one here is a quadratic function that interpolates these 3 points, this one and these 2. And then here it would be the same thing. Now the difference with quadratic splines is quadratic splines you made the derivative continuous between the different pieces. Here you don't care about continuous. Okay, so I can say that unlike quadratic splines, you don't make the derivatives of the quadratic pieces are continuous.
Is there a reason behind that?
Well, the reason behind that is that this formula is much easier. To do quadratic spline, you had to set up a big matrix and invert it. To do Simpson's rule, if you remember Simpson's rule, it's just you're adding points. There's no matrix inversion. Okay. So I can say that this rule is the basis of the Simpson formula. So I can say this specification is enough to determine Simpson's formula. I don't know. And if you remember Simpson's formula, you say the estimate is going to be if I don't know if I can remember what it is. I think it's 1/6 times. Is this right? I'll have to look it up, but I think it's f of x0 plus 4 f of x1 plus 2 f of x2. Maybe you can tell plus 4 f of x3 plus dot dot dot. And it goes 1 4 2 4 2 4 2 4 2 4 2, and then you get plus 4 f of xn minus 1, and then you get plus 1 f of xn, and then this is all times h, something like this.
It's h over 3.
H over 3? All right, thank you.
Yes.
But everything else is okay?
Yes.
Okay. Amazing. Okay. All right. Now this formula comes from this derivation. Okay. So this is kind of what's under the hood, is that you're thinking of this function as quadratic pieces, and you're piecing them together. Just like with trapezoid, you think about it as linear pieces, you're piecing them together. Now, the thing is that actually Simpson's rule is exactly the same as Romberg. So you can get Simpson's rule from Romberg integration. With intervals of size h and 2h. Right? Notice here that, as I said, you use a quadratic approximation on every 2. So if this is a h, then you also have the 2h. So the h and the 2h are treated differently. So in fact, if I did trapezoid on these h intervals, and then I did trapezoid on the 2h intervals, and I did Romberg on that, I would get exactly Simpson's rule. All right. So just to correlate what I said with what he, what is in the book, where is it? So I talked about Romberg. The next section is trapezoid, and he gives 4 different derivations of trapezoid. I don't think it's really necessary to read all of those. But I think actually the Taylor series one, as I said, is the more rigorous one. But you can read through these. He has some. It's good to see things in different ways. And you can see these pictures how the trapezoid works. So that's trapezoid. Then he talks about Simpson. He does the derivation of how Simpson is a quadratic. This took a little more than 15 minutes, didn't it? Whoops, this is trapezoid again. No, okay, no. Okay, yes. Yeah, so this is a long, you can see he's got a quadratic here. And he's going to fit this to these A's here are the quadratic fit. So you see it's quite complicated if you do it out this way. But these A's are the quadratic fit on one interval, and then he pieces them together, and a lot of the complication goes away, and you get this simpler rule here. You get this simpler rule like this. Okay, so he likes to derive things multiple ways. So he derives Simpson's rule a bunch of ways, right? And then he does some examples. So it'd be useful for you to look at that so you can do the quizzes. Okay, and then here's Romberg, and I think that his discussion is sort of like mine. Mine may be a little bit more hand-wavy than his. But he does the same kind of error cancellation. Right here he says ET is C over N squared, and then he does the error for twice as, so here he's doing the same thing. I2N and IN, right? So he's doing the very same thing. I2N is the twice as many intervals, and IN is with N intervals. Okay, so I think I can stop here.